group A is equal to, and this is the group, is the set. Now the set, this X in front tells you what values are you looking at. So what values? They can actually be points. It's possible for you to actually define a set of points as being the set of X and Y coordinates, so that something happens. And then after that we've got the condition, the thing that groups them together. And in this case we're saying 2 is less than or equal to X is less than or equal to 7. So this condition says which ones is this statement true for. That's how sets can be defined. Okay, so what numbers are in this set? What am I getting at? I am sharing this screen, aren't I? Looks like it, yeah. What's that point flashing for then? Oh, it's the graphing calculator. Yeah, it's just the integer numbers. This first line says, don't worry about fractions. So this is actually the list of numbers, and you will have seen me write curly brackets for just describing the numbers as 2, 3, 4, 5, 6, and 7. Group B, again, is the set of numbers of X such that we have 5 less than X is less than 12. And that should give us the list of numbers greater than 5 but not including 5. We're not worried about boundaries because we're only looking at integers. So the first one is number 6, 7, 8, 9, 10, 11, not including 12. And set C is the set of values of X where, and there are different ways people say things. They say things like such that, or where, or by is often used as well. So if you see such that or where, it's saying there is this description needs to match. This last one is 20 is less than X is less than or equal to 25. Okay, so that gives me numbers 21, 22, 23, 24, and 25, including the 25. All right, so that's the fairly basic, straightforward part of which numbers are included. Now, what we come into is describing groupings of these things. Now, the first group I'm going to give you is say what items are in A and B at the same time. So, what are the items that are in A and B at the same time? Well, I don't know why that's gone up there now. Go away. Yeah, it's only the 6 and 7. It's where these lists overlap and you don't repeat the values. Okay, Andre, it's not union. Union is the other one. So A and B is the intersect. And the intersect is written as an A with a hoop over the top of B. That's what you will see written often. So A intersects to B is the set of numbers 6 and 7. All right, that's the intersection one. It's where you can use the statement and. We're not saying what items are in A and B. That often confuses people if you use the word and, because they start listing everything. What we're actually saying there and is often used in logic to describe that situation is what items are in A or B at either time. Either time. And this will give us a union. And union, because of the, I wonder if this is just why it's called the union, or if this is where the symbol came from. The union is the loopy underneath. So it's not actually a U, it is a loop shape. So A union to B is everything that's in either A or B at any point. So it could be 2, 3, 4, 5, 6, and we never repeat a value. It's either there or it's not. It's not there twice. Okay? So we never repeat values. So we've got 7, 8, 9, 10, and 11. So that's the longest set. Now what you often get asked is, what's the number of items in these lists? So if you see an N, and it is a proper N, not an intersect sign, of A intersect B, or any set, it could be N of A, it's how many items are in there. So it's count the items. And that's why it's important that we never have repeating values. Okay, so if you do N intersect B, there's only 2 items in there. If we do the union, so if we actually count the number of items in A, 2, 4, 6. Number of items in B, 2, 4, 6. The number of items in A union B is not 12, it's 10. It's like we did what you do in probability. It's not, it doesn't matter, you don't double count things in the 2 places. So strictly speaking, what we can say is that the number of items A union B is less than or equal to the number of items in A plus the number of items in B. Okay, so it can never get bigger. You can't get bigger over the union. And the intersect will always be less than or equal to as well. That's a bit more obvious, that one. But the union one is saying it could be less than there is in the number of things if you add together the sizes. That's the first couple of descriptions. There's a second part. And I'm going to talk about a fourth set, D. And D is a set of numbers that X, where X is even and X is less than 12. Okay, so here's a new set for you, and I've actually got my conditions. The conditions are separated. It's an even number and X is less than 12, still perfectly valid. And that means that I can actually do some other bits and pieces with the sets. The first one I'm going to do is D. Do I want less than 12? Yeah. So D can be written as being part of the union of A and B. Now, is D bigger than the set of things in A and B, or is it smaller? So D is even numbers less than 12. And we're talking strictly positive integers as well, sorry. A union B is the numbers 2, 3, 4, 5, 6, 7, 8, 9, 10. 11. Now, is the size of D bigger or smaller than A union B? Number of items in D. Yes. That's not as, doesn't tell me what sign goes between the union. It's smaller. Yeah? So the number of items is smaller. And this is my tip for remembering the symbol. The symbol is to say we have is contained or is a subset, a subset, sorry. And this symbol I'm going to show you is actually the proper subset. And it follows the same rules as your less than sign, but we're now using the U shape on its side. So D is sort of on the smaller side of A and B together. It's the proper subset. The proper subset says that D is not the same as A union B. It cannot happen. If you were to allow that to happen, then a subset could be a set E could be a subset, any subset of A union B. And that means it could contain everything, or it could contain just some of the items. That's sort of less than or equal to. And that is any subset. If there's no equals on it, strictly it should be less than. There's not quite everything in there. All right, so that's one thing about subsets. If you turn it round, you're saying something is bigger than, but it must still contain the same things. So D, if you were to write it the other way round, we can say, where are we? There we go. A union B is a superset of D. And that just means it's bigger than. All right? So just be careful about those signs and what they mean. Next bit is the member of symbol. Now, member of is a bit like this subset. And a special case of it is when you're talking about just one value. So if we're talking about one value, like 6, I can say 6 is a value inside D. But as this is only one value, we put a line through it to say it is a member of. So there's one value, 6 is a member of D. When I post the notes up, I will highlight the keywords. So a member of. Okay, so 6 is a member of my even numbers less than 6. 5 is a single value. Why is that over there? It should be, oh, it's member. Yeah. So this is the membership sign. 5. So is 5 a member of my values D? Well, no. So to say not a member, or the opposite of, you put a line through. A single clear line to show not a member. Not in or not a member. Okay. So that's some of the horrible stuff you'll see with symbols that are going on with these. And I think I'll leave the Venn and Euler's until tomorrow, but we'll do one quick question again, and then I'll let you go get some practice on page 348. The last one is the example 2. So my example 2 is the set of polygons. And the reason we're doing this one is just to say it doesn't have to be numbers. We can actually do sets apply to objects as well. We don't have to be just talking about numbers. So my universal set is defined as being the set of all polygons. So give me a shape that doesn't fit this requirement. First point, give me some things which are not members of the universal set. What sorts of shapes are not polygons? Or what sort of things are not polygons? I'll give you a clue. A dog is not a polygon. Food, yeah, food is not a polygon. What sort of shapes though now? So we've done dog, we've done his food. I could do numbers, they're not polygons, unless I'm talking about the symbol itself. But what shapes don't fit into this stuff of being polygons? Is a cube. Yeah, cubes not. Yeah, we're getting them. Yeah, Arajan's gone for the more general one of mine. Yeah, all 3D shapes. Oh, sorry, I need to put that in another place. So dog is not in. Yeah, circle. I don't need to put an apostrophe on that one because it's a particular case. So a circle is not a member of the universal set. Yeah, the group 3D shapes is not contained within my universal set. Because this is a set over here. I'm comparing two sets, so is it a superset or a subset? No. 3D shapes is a set, but it's not a subset of my universal shapes. So let's write that phrase, just so you know that one. So we've got here, circle is not a polygon, not even a member of polygons. And this one actually said the set of 3D shapes is not a subset. So that's a subtle difference you need to be aware of if you're answering questions. Is if you're talking about one thing, one item, you can treat it as being a set, that's fine, or you can say it's not a member. If you're talking about groups, you need to talk about subsets. So it's not a subset of polygons. So that's some descriptions that you can give to them. So I've got a set A, which is quadrilaterals. There's the set of quadrilaterals. B is the set of triangles. And C is a set of regular shapes. So my question now is, how many things are there in the intersect of quadrilaterals and triangles? Think about what quadrilateral and triangle mean. Yeah, there are none. No items. And that's got a special notation. It means that the A intersect B is equal to, so it's equal to the following set of nothing. And to say that the set is empty is different to saying there's nothing. So A intersect B equals nothing is a proper statement. We are saying it is empty. And empty is 0 with a line through it. The reason that's needed is the set of 0 is actually not equal to the empty set. A set of values 0 on their own is not the empty set. And this is one of the things that led to Bertrand Russell not being able to formulate maths completely in the 1910s, was that they came to the condition, it was trying to work out, I have a set of, a list of lists, or all possible lists. Is that list within itself? And he could never resolve that using logical statements, which stopped him from being able to build mathematics from the most fundamental logic. If you ever have a look at that, it takes to about page 102 before he proves 1 + 1 = 2. That was Bertrand Russell and a couple of other people in about 1920s. They were trying to make maths completely universal. So it worked off all these basic tenets. Right, I'm fairly certain you're now in the position where you can do page 334. Describe the sets. Just so you're aware, we've basically done question 3 and most of question number 8. Question 8 has some extra bits for you, but I just wanted to use it because it was the easiest one to say this empty set idea. Empty. Okay. It is empty, and that 0 with a line through it says it's empty, not just it is 0. The number of things in it is 0. All right, you guys? So go page 348, exercise 18.1. Try and get familiar with the terms, the symbols that are being used. And I will try and post this up in a bit.